this is K Devender Reddy, Assistant Professor in Institute of Aeronautical Engineering, Jubilee Department. In this video, we are going to discuss about ratio of full load torque to the maximum torque and ratio of starting torque to the full load torque, and some numerical problems on torque equations, slip and speed of the induction motor. Generally, we know the expressions for torque maximum, starting torque, and torque under running conditions. So let us assume SF represents the slip at full load condition, that is full load slip. Slip at full load is equal to, I am assuming, as SF. So torque at full load condition I am naming as TF, which is proportional to slip at full load condition into R2 by R2 square plus slip at full load condition into X2 whole square. Torque at full load condition is proportional to slip at full load condition SF into R2 by R2 square plus slip at full load condition SF into X2 whole square. And maximum torque T maximum is directly proportional to 1 by 2 times of X2. So ratio of full load torque to the maximum torque, that is TF by T maximum, let it be TF full load torque may be equation number 1 and T maximum let it be assuming as equation number 2. So TF, ratio of full load torque to the maximum torque, which is equal to SF into R2 by R2 square plus SF times of X2 whole square divided by 1 by 2X2. So which is equal to ratio of full load torque to maximum torque TF by T maximum, which is equal to 2X2 into SF into R2 divided by R2 square plus SF times of X2 whole square. TF by T maximum equal to, make some constant, take it as a constant, 2X2 into SF into R2 by X2 is a common, R2 by X2 whole square plus SF square. Now this is equation number 3. Now both numerator and denominator has to divide with X2. Both numerator and denominator should divide X2. So this will be TF by T maximum equal to 2 times of divided by X2 square, 2 times of X2 by X2 square into SF into R2 divided by R2 by X2 whole square plus SF square. This will be 2 times of SF into R2 by X2 divided by R2 by X2 whole square plus SF square. Let us assume A equal to R2 by X2. So simply substitute A equal to R2 by S2 in the expression, that is TF by T maximum, which is equal to 2SF into slip at full load condition into A by A square plus SF square, where A equal to R2 by X2, that is equal to slip maximum corresponding to maximum torque T maximum. So in this expression we can also substitute TF by T maximum which is equal to 2 times of Sm slip maximum into slip at full load condition by slip maximum square plus slip at full load condition square. We will have a ratio of full load torque to maximum torque, that is 2 into slip at full load condition into A, that is A equal to ratio of R2 by X2. We know that slip maximum condition, slip maximum Sm equal to R2 by X2, where this value will be equal to the maximum torque condition. So we replace the A with respect to the slip maximum Sm, we will get ratio of Tf by T maximum equal to 2 slip maximum times into slip at full load condition by slip maximum square plus slip at full load condition. Similarly, derive the expression for ratio of starting torque to full load torque Tf. Similarly, derive the expression for starting torque to full load torque. Let us assume TST, that is the starting torque, is proportional to R2 by R2 square plus X2 square. Slip at full load condition Tf is proportional to, TST by T maximum. Let us derive the expression for TST by T maximum. So T maximum, we have a relation is directly proportional to 1 by 2 X2, right? That is T starting by T maximum, which is equal to 2 times of R2 X2 by R2 square plus X2 square. So similarly, both numerator and denominator should divide with the X2 square. We will get 2 times of R2 into X2 by X2 square. Here R2 by X2 whole square plus 1. So here X2 and square cancel. So ratio of starting torque to maximum torque T maximum, which is equal to 2 times of R2 by X2 divided by R2 by X2 whole square plus 1. So similarly, naming it as A equal to R2 by X2, ratio of resistance to the reactance of the rotor, and TST by T maximum starting torque to the maximum torque ratio 2 times of the A by 2 A square plus 1. This is another relation for torque. So we'll discuss some numerical problems on torque derivations and how to calculate the slip and as well as the speed. A 4-pole 3-phase 50 Hz induction motor. Calculate the frequency of a rotor current for the following conditions. At standstill, motor running at 500 rpm in same direction. This is a mistake. Same direction as a field. Motor running at 500 rpm in opposite direction as a field. Motor is running at 2000 rpm in the same direction as field. So here in the problem we have, it is a 4-pole machine. So given data, it is a 4-pole machine. Number of poles are 4 and the frequency is given 50 Hz. Right. Then there are 4 certain conditions. In 4 conditions, we need to calculate rotor current, calculate the frequency of a rotor current for the following conditions, calculate the frequency of rotor current for the following conditions. So first condition, at the standstill, so generally the expression for synchronous speed is equal to 120 F by P. This is 120 into number of poles and number of frequencies 50 Hz and number of poles are 4. It becomes 1500 rpm. That is synchronous speed of the rotating magnetic field is 1500 rpm. Now slip, calculate slip equal to ns minus nr by ns. That is at standstill condition slip becomes 1, and that is at standstill condition nr equal to, this is 0, So ns by ns, that is equal to 1. So rotor frequency Fr equal to, we have a formula, slip times of the frequency of the stator. So Fr equal to, slip is 1 time of the Fs, so that is equal to 50 Hz only. At standstill condition, rotor frequency Fr equal to stator frequency. Second one, motor running at 500 rpm in the same direction as field. So now the rotor speed is 500 rpm, which is of same direction as the magnetic field direction. So calculate first slip, which is equal to ns minus nr, ns minus nr by ns. So ns is 1500 rpm and it is a 4-pole machine and it is running at 1500 rpm, and nr is 500 rpm divided by ns is a 1500 rpm. You will get slip equal to 0.66. And similarly calculate frequency of the rotor induced EMF equal to slip times of the frequency of supply. Slip is 0.66 times of frequency of the supply is 50 Hz, right? You will get 32.33 Hz. Next, third condition. What is the third condition? Motor running at 500 rpm in opposite direction. So NR becomes 500 rpm, but it will be opposite direction of the magnetic field. So slip equal to now ns minus of minus nr, that is a opposite direction, ns. So it is ns plus nr by ns. So it is ns speed of the synchronous magnetic field 1500 plus nr is 500 divided by 1500. So it is 2000 by 500. 2000 by 1500 will get 1.33. Slip equal to 1.33. It is greater than 1. So it is comes into the generating mode. Next, frequency of the rotor equal to slip times of the frequency of the stator, that is 1.33 times of the frequency of the supply. It is 50 Hz. We will get 66.5 Hz. And the last condition, fourth condition, what is that condition? Motor running at 2000 rpm in same direction as a field. So nr is equal to 2000 rpm. It is more than the speed of the synchronous magnetic field speed. So slip equal to, it is 1500 is the synchronous speed minus 2000 rpm is the speed of the rotor divided by 1500. We will get some negative slip. So the negative slip is around minus 0.33. And similarly, frequency of the rotor equal to s times of the frequency of the supply. So Fr equal to minus 0.33 times of 50 Hz. We will get minus 16.6 Hz. So in this discussion, we have slip equal to 1 at starting. When speed increases to 1500, this is ns. Slip is in between 0 to 1. This is when speed reaches to, rotor speed reaches to the synchronous speed. Slip becomes 0. So in this, we have motoring. In this, we have motoring mode. If slip is greater than 1, it is a braking mode. The previous we talking about generating mode, not the generating one. It is braking mode. If slip greater than 1, it is braking mode. If slip less than 0, that is negative values, it is generating mode. Another problem, a 300 volts, 24 poles, 50 Hz, 3-phase star connected induction motor has a slip ring rotor of a resistance 0.016 ohms and standstill reactance of 0.256 ohms. Full load torque is obtained at a speed of 247 rpm. Calculate ratio of maximum torque to the full load torque. Speed at maximum torque. Neglect stator impedance. So the given data in the problem: a 300 volts, 24 poles. Number of poles are 24. Frequency is a 50 hertz. 50 hertz. Three-phase star-connected induction motor has a slip-ring rotor resistance. So rotor resistance is 0.016 ohms, and standstill reactance X2, which is equal to 0.256 ohms, and full load speed NR equal to 247 rpm. So calculate ratio of maximum torque to full load torque and speed at maximum torque. Neglect stator impedance. So in this case, first of all, find out slip at full load condition, SF equal to NS minus NR by NS. So it is NS is 24 poles. First calculate NS. NS equal to 120 into F 50 hertz by number of poles are 24. So it is around 250 rpm. So slip at full load condition SF equal to 250 minus speed of the motor at full load condition is 247 rpm divided by 250. We will get, simplify this and we will get 0.012, and then slip corresponding to the maximum torque, that is A equal to R2 by X2. So R2 is already given, that is 0.016, and X2 is given 0.256, and simplify it, we will get 0.0603. Then after, ratio of maximum torque to full load torque TF equal to 2A square plus SF square by 2A into SF. So it is A square is 0.0603 square plus slip at full load condition 0.012 divided by 2 times of 0.0603 into 0.012. Simplify this and you will get T maximum equal to 2.615 times of torque at full load condition. Similarly, the second case, speed at maximum torque. So slip equal to NR minus NM, NS minus NR by NS into 100. So NS is 250 rpm minus NR by 250. So into 100, we will get slip equal to 0.6038. So substituted, you will get NR equal to 235 rpm. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.